Birefringence is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light. These optically anisotropic materials are said to be birefringent or birefractive. The birefringence is often quantified as the maximum difference between refractive indices exhibited by a material. Crystals with non-cubic crystal structure are often birefringent, as are plastics under mechanical stress. We can observe this property if we place a calcite slab over a sheet with text. We observe double and single diffraction of light as we rotate the calcite slab on the sheet of paper. Birefringence is responsible for the phenomena of double refraction, whereby a ray of light, when incident upon a birefringent material, is split by polarization into two rays taking slightly different paths. Now we will conduct the experiment to demonstrate the phenomena of birefringence. In the first part of this experiment, we will pass a monochromatic beam of light from the laser through the optical path, which consists of the analyzer, the polarizer, and finally the lux meter, which will receive the final beam. In the second part of the experiment, the setup will remain the same, but with an addition of the sellotape film between the analyzer and polarizer, which will act as a birefringent material. Here we can see the setup for this experiment. Starting from the left, here's the laser, the analyzer, polarizer, and the lux meter, which will act as the intensity detector. And on its screen we can see the intensity that it's measuring. So initially the analyzer and polarizer are both at 0 degrees. We will observe that when we change the angle for either of them, the intensity of light changes. Here I change the analyzer's angle by 5 degrees. Here I change the analyzer's angle by 10 degrees. And we observe a change in intensity. If you change it again by 10 degrees, then again you observe a change in intensity. So that we proceed with the experiment by changing the angles by 360 degrees, 10 degrees as each reading, and we measure the intensity. We note down the intensity measured by the lux meter every time we change the angle. You can see the intensity at the lux meter, and we note that down. Now, with respect to the polarizer, the angle of the analyzer is 180 degrees, and you can observe the change if there is any. Now I change the angle to 180 degrees, not 360 degrees. this is at 0 degree. That's 90, and here we observe minimum light intensity. Intensity increases again, and it's maximum at 180 degrees again. Then to 70 degrees. We again see minimum intensity. So I'll skip the in-between readings, but that will be on the same day. So here we saw that there was a pattern, that the intensity of light after passing through the analyzer and polarizer changed in a particular pattern. Now we'll conduct the second part of the experiment. Now we begin the second part of the experiment, in which we will introduce a film of sellotape between the analyzer and polarizer. So we will use an orbital sellotape, and I am using this. For the second part, I have stuck a film of sellotape on the analyzer, and you can even use a proper stand to do that, but even this works. Now in the previous part we saw that light intensity from 0 to 90, its maximum at 0, it decreases till 90, then from 90 again till 180 its maximum, it increases, and at 180 its maximum. Then 180 to 270 it decreases, and 270 its minimum, and 270 to 360 it increases, and its maximum at 360. But by introducing the sellotape film, we observe some changes. Now the intensity that we see right now, the polarizer is at 0 degrees with respect to the analyzer, and when we change the angle, we observe a change in the intensity. This is the change in intensity at 10 degrees. Then we'll take 20, 30, but right now I'm taking it directly to 90. However, it's best to take all readings without skipping any. Okay, so when the sellotape film was not involved, we saw that at 90 degrees the intensity would become 0, but here we see that it is not 0, it is neither maximum nor 0, but somewhere in between. Again, at 180 degrees it should become maximum, but let's see what happens. Even at 180 degrees it's not maximum. Then at 270, here it should be minimum, but we can see that it is not. Now back to 360. Here we see that light intensity is minimum at a point if that is not in a fixed pattern. Here we see intensity is at minimum at 305 degrees. Then increasing, and again it decreases, and here it's minimum at 220 degrees. So again we'll do that, increasing, and I guess this is maximum, and maximum we're getting at 165 degrees. Here again it decreases. So at the end, when we change the angle by 10 degrees each and take a reading after we changed the angle, we observe change in intensity, but that is not in a particular pattern. So this is when the properties of the property of birefringence of this sellotape film comes into play. In this experiment, we observe the birefringent property of sellotape. In part 1 of the experiment, when light is passed through the optical setup, we see that the intensity of light changes with respect to the angle of polarization in a particular pattern. But in the second part, we see that the sellotape film is introduced in the optical path. The light intensity changes with respect to polarization angle, but we do not observe a particular pattern, and intensity changes in a haphazard manner. This is because when the sellotape film is stretched, its particles are relocated, and hence the refractive index of that section of the film changes. That is, the refractive index of the sellotape film is not constant throughout its length. Therefore, due to the birefringent character of the sellotape, light rays diffract in different directions. Hence, we observe the phenomena of birefringence.